All right. Hello, everybody. Oh, come on, it's summer. We need to hear a little bit more enthusiasm than that. Hello, everybody. Who's ready to learn a little bit about astronomy tonight? Who's just here for the food and drinks? As those of you who've been here in the past often know, we like to just find out who here is new. So how many of you have never been to Astronomy on Tap? All right, welcome. Very cool. Give these guys a round of applause for their first time. How many of y'all have been here at least once before? How many of y'all have been here at least 5 times? All right, the regulars. Well, welcome back to those of you who've been here in the past, and welcome for the first time for those of you who are here. We're going to tell you a little bit about what this event is before we jump into all of the fun science and space. My name is Tracy. I'm one of the co-organizers, and we have...
Aaron Deleon.
Michael Valles.
Samuel Hart.
And we have Adam and Brian on our video and sound, and Thomas is virtual. Okay, do you have this slide clicker?
All right, so what is Astronomy on Tap? Many of you know already, but for those of you who are new, it is a worldwide phenomenon. As I like to say, we have locations all over the globe, not just in the United States. It did start in Brooklyn, New York, but it has expanded much from then. And we here have existed for 5 years, so yes. And our Astronomy on Tap, the best ways to describe it are that it is fun. You will have fun tonight. It is interesting. Both talks are going to be really cool, and one of them, as you have all been given, will have a fun demonstration and interesting. It's interactive. You all will have an opportunity to ask questions at the end of the talk, but we have the number up here on the TV screen that you can message during the talk as you think of your questions, so please use that. And at the end, you will have a chance to win. We always do trivia every time, and we have some great prizes today, including some Celestron merchandise and some cool stickers that Sam will pick out at some point. You didn't get the stickers. We also have eclipse glasses for those of you who haven't picked something up already. We have eclipses coming up, so we've got those for you. And please be sure to check us out on our socials. We've got pretty much all of them. So check us out, follow us, keep on coming. Tonight?
Hello, everybody. Today we have 2 excellent talks and some astronomy in the news by our resident amateur astronomer, Caleb Gamar. Our schedule tonight, first, both of these speakers have very long titles. The first one, the Prism that will be hopefully, how do you pronounce that? XRISM. Trying again by Dr. Eric Schlegel, and he is giving us a demonstration on spectroscopy, which is why you've got your little monocles. Next will be astronomy in the news, and finally, Aaron Deleon, Surrey UTSA graduate student, will be talking about shaping the future, utilizing the Arecibo telescope and SHAPE to learn about asteroids. So, without further ado, let's introduce our first speaker. Dr. Eric Schlegel got his Bachelor's of Science from State University of New York, SUNY, I believe they call that, and then his Master's and PhD at Indiana University in Bloomington. From there, he went to Goddard Space Flight Center, worked there for a few years, and then Chandra X-ray Observatory launched, and he started working at the Harvard Center for Astrophysics. At some point, I'm only reading his UTSA page, so I don't know everything here. At some point, he found his way to UTSA, where he studies binary stars that are interacting with one another, supernova, and the topic of this talk, X-rays. Dr. Eric Schlegel, everybody. That's okay. Hopefully you don't say it too much. Eric's drinking word is?
Prism.
Prism. Not chrism, though, so don't woo chrism. Thank you. Oh, yes. Say it one more time.
Prism.
Very nice. All right. Thank you.
All right, good evening. I'm assuming that most of you do not know anything about spectroscopy, so that's why we're going to do the demo here. This is very much a spectroscopy subject. Oh, and I will explain at the end why the title is structured the way it is.
Eric.
Sir. First off, we want to look at the electromagnetic spectrum. All right? So long wavelength is down here. Short wavelength is up there. You can think of it in frequency, energy, wavelength. Doesn't matter which one you use. Pick one, stick with it. The words are rough descriptors. What I'm talking about is, oops, sorry. I grabbed the wrong button. What I'm talking about is up here. And of course, we're down here. The one thing to remember about this is that from the blue side of the optical spectrum to the red side is roughly 1 octave of frequency. The X-ray band is more like 5 or 6 octaves. Consequently, there's a lot of stuff that you have to think about when you are dealing with that broad a frequency range. If we could see 5 or 6 octaves, we would go all the way out to the point where you would see every person glowing at 98 Fahrenheit, okay? So that's well into the infrared. And so the X-ray band is very broad. All right. So a rough rule of thumb. If you think of a seesaw, right? Radio is down on this end, X-ray is on that end. All right? The number of photons is opposite. So you get a lot of photons in the radio. You get very few photons in the X-ray band. That's a problem. All right, so we can measure these properties from X-rays. Position of the X-ray, depending on how good the telescope is, the energy of the X-ray, the arrival time, and polarization. The very first thing I'm going to do is take polarization off the table, because that would be a completely separate presentation. I'm also going to take the arrival time off the table because we've been able to do arrival time studies since the very first X-ray mission went up in the 1960s. It's not that hard. You set a clock, you can do it. And most missions can cover the timing. They aren't built to do that. It just happens as a result of the detector. All right, so we're looking at position and energy. So one of the things that I want to get across tonight is why is this mission called XRISM so interesting? And that means we need to understand better spectral resolution. And I'm going to do that by going down 2 paths. One path is going to be resolution, the other path will be spectroscopy. So that then at the end of that, hopefully you can combine the two and you understand what the value of this mission is. All right, so the history of X-ray astronomy is gradually we get better at measuring X-rays. It didn't happen all at once. The very first X-ray telescopes were called proportional counters. They were basically a big box of gas and wires. Well, X-ray would come in, hit an atom. ionize it, then that would be attracted to the wire, and you would measure the change in current, and you would know you detected an X-ray. Remember, we're detecting X-rays that are coming to us. We're not shining X-rays out to anything, all right? I get this a lot because too many people think of X-rays, they think of dental X-rays or medical X-rays, and you stick your arm or your teeth into the beam. It's not what we're doing. We are detecting things coming to us. The sun is an X-ray source. Luckily, not very bright one. It's bright because it's close, but it's not really that bright in the X-ray band. If it was, we'd be in trouble. So the problem with a proportional counter is that it's not imaging. You're just detecting the X-ray. And if the wires are, you know, 1/4 of an inch apart, 1/4 of an inch down here in the detector is a big spot up there. And so you're not really doing a good job in measuring position of X-rays. So then people started looking into electronic devices. Charge-coupled devices were used in early cell phones. Nowadays, you're using a different technology, so it's less battery intensive and all that sort of thing. But the early detectors were CCDs. Chandra has CCDs on board. How many people have been to a dentist recently? By recently, I mean past 3 or 4 or 5 years. All right, almost everybody. You've gotten the little thing that they put inside your mouth that then displays right onto the TV monitor. That's a CCD. Why is it available to you now as a dentist? Because of Chandra. They started working on those detectors in the 1980s. And now it's gone out into the dental world. What's the value to you? Because you're not using film anymore, you can turn down the intensity of the X-ray beam. And now you're not damaging the cells in your cheek or gums or whatever nearly as much as you were when it was just film. All right, so I've got a series of slides here of what better resolution in terms of imaging does for you. So on the left is a galaxy. This is NGC 6946. If you're a galaxy person, this is a famous touchstone galaxy. We could talk about another complete talk about why. We'll skip that for the now, but that's an optical image. On the right is an X-ray image with the Einstein satellite that was launched in 1978. If you're sitting there thinking, I don't see a galaxy, welcome to the club. All right, next slide. This is ROSAT, 1990, a German, US, British collaboration. Now you can start, hey, I actually see a little bit of a galaxy there. And then Chandra. Pretty much every black spot you see on that image is an X-ray source in 6946 or behind it. And so this is what better resolution does for you in terms of imaging. Now, what we want is the same increase in spectroscopy. We can, historically, detectors have poor resolution because measuring the energy of an X-ray is hard. Measuring the energy of the optical is hard. You just don't have the technology to do it until relatively recently. So, what do I mean by spectra? Could we use CCDs for spectroscopy? Well, the answer is not really. This is the typical X-ray spectrum using
Testing, testing.
See how far I can pace. Is this broken here? Or is it just loose? Okay, just wobbly is good. All right. So what we're looking at is a CCD spectrum. So low energy, low energy on the left, high energy on the right. Maybe here or here there's an emission line. Maybe. But you wouldn't really conclude that from that spectrum. So the question then is, what do I mean by spectroscopy? So at this point, I need lights out. I need, we want to get the gratings into our hands. And yeah, it might take a few minutes for the lights to go out and all that sort of thing. All right, so if you hold up the CCD right now, orient it so that it matches this black TV screen in terms, so, you know, longwise horizontally. All right? Now, I'm going to turn on this light here, or not. What did you guys do to my power source here?
No, it's on.
No, there. Okay. All right, so if you look at this thing, you should see a continuous spectrum. Yes? And by continuous, I mean all colors of the rainbow. Yes? All right. Let me now go to, what is going on here? Okay. All right. Now, is there any way to temporarily turn off the screen here? All right. So now you should see a line in the red, a line in the bluish green, and if you are relatively close to the lamp, you should see a line in the purple. Yes? No? Okay. All right, so the advice is if you've got glasses, take them off and you might be able to see better. All right? And if you are in the back and you don't really see anything, we'll have this on the break and you can come up and get a lot closer and look. All right? What you're looking at is particular transitions from a higher energy level to a lower one. And the different lines are different sets of transitions. Now, this is one line, this is one gas. Let me show you a different gas. And you should see a different pattern. Yes? What do you see? All right, green, purple. All right. All right, I'm going to, so my guess is you've gone to establishments other than this one where they have names in glass tubes, yes? What are those called? Neon tubes, yes. So, you've seen them in different colors, I presume. Yep. If they're not this color, it's not neon. This is neon. And so you should see a whole slew of lines in the red. All right? Previous gas was mercury. And the first spectrum I showed you was hydrogen. And you know, the break or at the end, we can look at helium, we can look at carbon dioxide. Those were the only ones I brought with me. All right, are we okay on the spectrum then? So you get the idea of a line. Yes? All right, let's go back to the slides. We can bring the lights back up so that poor waiters don't trip over feet and everything else. All right, so you can use a prism. My guess is, I knew, I forgot that was the word, sorry. You can use a triangular glass shape to disperse the light. My guess is you've played with one of these triangular glass shapes at some point in your life. You can also use a grating, which is what you were using here. The grating has got a bunch of lines on it. The lines diffract the light. And so what we were looking at was essentially these kinds of transitions. We were looking at these kinds of lines. They're emitting light because the electron has gone up a level for whatever reason, drops down, lets off the light. And that's what we were seeing with the gratings. The problem with all of this stuff is you are dispersing the light. And in astronomy, if you disperse the light, the only thing you can do is expose longer, because you need to build up a certain amount of signal that exceeds the noise. And if you don't get there, then you haven't really detected anything. So dispersing the light in astrophysics is a pain in the posterior. All right? I use the word pita to describe that. That means you're automatically blurring out velocities. So if you've got two stars going around each other, you've just blurred out all that motion, and you lose that information. So you don't really want to disperse the spectrum. We measure this by the wavelength divided by how accurately we can measure. So CCDs give us a value of this ratio of about 20. You can use gratings, really high quality gratings. Chandra has 2 on board, and you can get
Whew. Okay.
all right, so I will now hold it at the bottom of the... Nice try. So gratings will often give you a value of about 60 up to 300. Remember, we have a broad range that we're covering. And so it depends on where you are in that energy range, what that ratio is. But there would be an improvement. Could we measure the energy of the X-ray directly? And the answer is, we're going to get about the same resolution as the gratings, but we're not dispersing the light. And therefore, we get better signal to noise in a lot less time. Therefore, we can start to measure motion. We can start to look at temperature behavior and things like this. So what we're talking about here is a calorimeter. And this is the calorimeter detector, the detector plane. Now, if you look at this and think, well, that looks like a 6x6 grid, yep. So we're not talking about high resolution imaging here. We're talking about high resolution spectroscopy. This is, I'll explain a bit in a moment why we have this data, but this is a spectrum from the Perseus cluster. Perseus cluster is a big cluster of galaxies, a lot of hot gas in there. And the red line is the best previous spectrum of Perseus. The black line is with a calorimeter. And you can immediately see the difference. I mean, for example, right here, you don't get to measure this behavior. You get this lump. Now, what does that gain for you? You get to measure the positions of the lines, line strengths, widths of the lines. We can derive temperatures, densities, velocities, possibly even magnetic field strength, which would be a big deal. We might even help with lab-based atomic physics. The problem so think about the periodic table. You've got hydrogen, 1 electron, helium, 2 electrons, and so on. It's easy to measure certain of those elements, the properties of those elements, because you can reproduce in the lab hot gas. It's hard in certain areas, like mid-range iron. If you've ionized iron by a factor of 14, so you've ripped away 14 electrons, the difference between 14 electrons and ripping away 15 electrons, or 13, is not that much. And so trying to measure the properties of iron 15 is hard, because all of that stuff ends up being in the gas at the same time. In astrophysics, it's trivial, because it's all out there and we just measure it. Now, why did I put the try in the title? Well, I think by the end of this, I will have everybody weeping into their beer. All right? Ready? This is going to go somewhat quickly. Asteroid, 1999, went into the ocean. Suzaku, 2005, the Dewar failed. You need cold gas to keep this calorimeter working. They built the Dewar improperly. It wasn't the people that built the calorimeter that built the Dewar. They didn't do a good job. Cooling gas lost. Hitomi, 2016. There was a sign error in the pointing algorithm and the satellite spun out of control. Before it spun out of control, because this is launch number 3 of this calorimeter, they had put it into orbit such that they would get data on Perseus. All we have to do is open the door. We get data on Perseus. And then they said, oh, great, it's working. Zoom, and it fell up. XRISM, launch scheduled for late August. Now, from a personal point of view, all right, when you put in for science observations on any of these missions or any other, Hubble, JWST, whatever, you write a proposal. And it's judged by your peers, and if your proposal is given a high ranking, you get time, and you pat yourself on the back and go, all right, cool. And historically, I have tended not to win cycle 1 time. I have no idea why. I've laid my proposals down next to the people that win, and I think, well, I don't get it. There's something about the way I phrase something or whatever. I do fairly well. I've got probably a 30 or 40% success rate with proposals to satellites, just not cycle 1. I had cycle 1 Astro E time. I have been waiting 24 years for this mission to get into orbit. Pardon me? Persistence. It's persistence. So, as unscientific as it sounds,
What's the launch?
I hope it makes it to orbit.
What's the launch
So that's, thank you. So the launch vehicle, the reason why there's a question mark on the late August schedule is the launch vehicle is so this is a Japanese-US mission. US contributed the calorimeter, the Japanese have built everything else. Japan has had a tremendous success rate on all missions not carrying a calorimeter. Seriously. The rocket that XRISM is supposed to go up on had a problem in the previous mission. And so they're taking extra caution and saying, let's make sure that this one gets there. So I'm hoping it gets there.
All right, thank you. That was a really cool talk, and the demonstrations are really cool. And you said we can put them on again during the break? All right, perfect. All right, so first question. Will XRISM, not Prism, have a high enough spatial resolution to observe extragalactic objects like nearby active galactic nuclei, or will it only have a sufficient enough resolution for objects within the Milky Way?
No, the mission is built to look at a broad range of things. The resolution will be roughly, hold on, let me go back to, the resolution will be probably about like that for imaging quality.
Thank you. Does the motion of a subject affect resolution and image quality for X-ray images in the same way that it does with visible light?
Sure. But in general, things in the X-ray band are, they're either moving very rapidly, and so you detect that, or they're not moving at all, and you don't detect any motion. So.
Reminder, the number's up there to text in questions if you have any. I'm waiting on them. If anybody has one, I guess.
How do you shield
there we go.
the instrument? All the X-rays coming from directions you don't want to look at.
How do you shield the instrument from X-rays and all other directions you don't want to look at? That's for the people online.
Oh, got it. So the instrument is pretty well shielded in the sense of you build up enough material around the detector that absorbs the X-rays coming in from other directions. One of the problems with Chandra at the moment is that because it's been up there since 1999, some of that shielding is starting to degrade. And therefore they can't point Chandra at just any object for just any amount of time. They have to really manage where it's pointing so it doesn't heat up the instrument too much. And this is part of the problem in the X-ray band. You really have to manage a broad range of things in addition to just managing the angular momentum of the satellite.
What is cycle 1?
What is? All right, so NASA does things for satellites roughly on year boundaries. And so the first announcement for proposals is called Cycle 1. And what they did for Asteroids was they held a proposal opportunity before they launched it. Oops. Since then, they have not held a proposal opportunity prior to launching, which was smart. Yes, JWST did, yes. But, they thought they would get that one off the ground. I was skeptical. I'm glad it does. I'm very glad JWST works because, so I was at a science conference in 2018, I think it was, called Space the space astrophysics landscape in the 2020s. And the high energy people are unhappy with the infrared community because it's been infrared mission after infrared mission after infrared mission. Chandra is 25 years old. Fermi, which is a gamma ray satellite, has been up there since 2007. SWIFT, which is an X-ray rapid repointing mission, has been up there since 2006. They're all aging, and there's nothing on the drawing boards. And it's like, brr. So, other questions? Yes? Oh, somebody that knows X-ray instrumentation. So the question was, essentially the question is, how do you focus X-rays? So the way you do it in the optical is a mirror with a concave surface. And the X-rays, or the light comes in and hits the surface and comes to a focus. In an X-ray telescope, the X-rays would go right through that, and you would not have any focus. So the way that X-ray telescopes work is you've got basically a cone. And so you're essentially deflecting the X-ray in the same way that you skip a rock off smooth water. And consequently, because those mirrors have to be a lot bigger, even though they're not very much larger in diameter, it's very expensive to get that quality. The Chandra mirrors would cost easily $1 billion today, just the mirrors, not the rest of the telescope. And so I was at NASA Goddard about 2 weeks ago and talked to a guy that he's working on improving how you build mirrors. And it's like, cool, because he would cut that cost by at least a factor of 10 to 20 today if he could do it. So they're thinking ahead and coming up with next generation of mirrors. Other questions? So Chandra's mirrors are glass with a gold and iridium coating. The mirrors that are being developed at NASA Goddard right now are pure silicon. I mean, they just slice them and buff them. I was like, wow, that's impressive. Other questions?
One more from the phone. The last question. One for the road. Your initials are the same as electromagnetic spectrum. Do I need cool initials to be a successful astrophysicist? Let's thank our speaker once again. Whoever sent that one in, that A+. Oh, yes. We are at our break. We will take a 10-minute break. Get your refills, get your food if you haven't already. Come check out our merchandise up here. We will return at 7:40. 50. Sorry, it is 7:40. We'll return at 7:40. And be sure to sign up for our email list if you haven't already.
7:50.
Did I say 40 again? 50.
Come up and is that actually? I don't know.
Merch and All right, everyone, let's settle back in. What? All right. We are moving on to the second half of our program tonight. As always, we have our Astronomy in the News segment presented by UTSA SWIRI student Caleb Guimar. Please give him a round of applause.
All right, well, good evening, everyone, and welcome to another edition of Astronomy News. So, first and foremost, what is in the skies of June? Well, if you go outside about mid-month around 10 o'clock p.m., this is what the sky will look like approximately. You still have a couple of planets very well placed in the early evening sky and throughout much of the rest of the later part of the evening, as a point of fact. Venus is actually at about the highest it will be in the evening sky throughout the remainder of the year right now. It actually reached greatest eastern elongation basically a few days ago. It was just over the weekend. So if you go outside, look over toward the west, you will see a very, very, very bright star-like object over toward the western part of the sky, again, the setting sun part of the sky. That is indeed the planet Venus. If you have a telescope or even a really fairly powerful pair of binoculars, you can look at the planet Venus and you'll actually see that it looks a little bit like a quarter phase moon, except it's really, really bright in the field of view. Yes, you actually are seeing the part of the daytime side and part of the nighttime side of the planet Venus. It is one of only two planets in our solar system that we can really see that from the Earth very well, that being Mercury as the other one. So do get a look at Venus during this time of year. It's a very good time to look at it. Mars is very close to Venus in the sky during much of this month, and it will continue to wander over more toward the western part of the sky, so it's going to be very small, not as bright as it was during the winter season. So do get a look at Mars now while you still can, because it will get farther and farther away from us and dimmer as the months go on. Now, a deep sky challenge for you. Look over toward the south. And toward the south, there's this kind of odd assortment of stars as Centaurus, the Centaur. And if you're out in a very dark sky with a very clean horizon, not a lot of trees or hills in the way, look with a pair of binoculars right in between these two stars here in Centaurus, and you will see a little fuzzy spot there. And it's actually, in a very dark sky, quite a sight. Through about a moderate-sized backyard telescope, probably 6 to 8 inches diameter backyard telescope, you will actually be able to see a bunch of little glittery stars in this fuzzy patch. This is a globular star cluster, a group of very, very old stars that's kind of what you would call a galaxy within our own galaxy, if you want to call it that. It's probably not the most accurate terminology, but nonetheless it can be used here. This group orbits the core of our galaxy. It is about 15,000 light years away, and it is probably one of the best globular star clusters to observe in the sky. And oh, by the way, only in more southern latitudes do you see this globular star cluster. If you go up much more northward than the state of Texas, you start losing it on the southern horizon. So we are very, very fortunate to be able to see Omega Centauri, this really spectacular globular cluster from this area. So definitely take a look at that if you can. So now on to the news segment. The first news story I'll cover is the fact that they have actually found evidence of a polar vortex, a polar cyclone, I should say, at the planet Uranus. So how many of you have ever seen the pictures of the polar cyclone at Saturn? Yeah, or a really unusual looking formation, isn't it? Well, they found evidence of something very similar to this at Uranus. So using data from the very large array, that a large grouping of radio telescopes in New Mexico, a group of astronomers has found evidence of warmer and drier regions toward the polar region of Uranus, and these are the images that actually show these differences right here. And that indeed indicates a polar cyclone here. So a very fascinating finding on that very distant ice giant world. Now, going to a infrared band observation from the James Webb Space Telescope, yep. An observation of Saturn's moon Enceladus has revealed a very large water plume emanating from the surface of Enceladus. Now, this phenomenon was known before. In this image from Cassini, you can see these plumes, but what was not known was the whole extent of how far these plumes go out. What James Webb Space Telescope was able to observe was these plumes extending out to 6,000 miles. Now, the moon itself is only about 300 miles across. So that's quite a ways out there. And this water is being fed into a torus around Saturn, towards its outermost ring boundary there. So this water that is escaping away, actually 30% of it is trapped in that torus, and JWST was able to return spectra showing that water signature. So again, very fascinating data concerning Enceladus. So now for the high energy end of the spectrum, something we just heard about from Dr. Schlegel in his talk, from Chandra X-ray Observatory and a few other telescopes, as a point of fact, observations have been made of a series of galaxies basically being captured and brought into the Coma cluster. So Coma cluster is a very, very condensed, very massive galaxy cluster. And in this image, you see a shock wave in front of the group of galaxies that's moving toward the core, the heart of that galaxy cluster, and a very long tail of heated material moving away. Now again, what was really surprising about this was the extent to which this heated material goes away, this tail of material, about 1.5 million light years long. That is a really, really long distance out there. And this series of images gives us a lot of insight into the evolution of galaxy clusters over time. So not only a very pretty sight in the images, but also certainly a very important finding for understanding the scale and structure of our universe. And then finally, how many of you have heard of this one, the supernova that was recently observed in M101? Yes, indeed. So there's a few of you that have heard of this one. So not too long ago, an amateur astronomer in Japan observed this supernova in a nearby galaxy, M101. So every once in a while, you can see these supernovae take place in these nearby galaxies. In fact, in our own galaxy, these kind of events are very rare, so we never see a lot of them within our galaxy. But if you observe many more distant galaxies for a while, you'll eventually stumble across one every once in a while. But this one is special because this galaxy, again, is a little on the closer side. It's about 21 million light years away, if I'm not mistaken. So quite a ways away, but not as far as it could be. And certainly everyone is taking a very close look at this and understanding as much of it as possible while it is visible. So just for those of you out there that are thinking of picking up amateur astronomy as a hobby, you can do significant science also. It can be done. So do bear that in mind. So just my usual heads up about the eclipse coming up, actually the two eclipses coming up, the annular coming up in October and the total solar eclipse coming up next April, all right? Now, I am going to give progressively more detail on this as these presentations go on throughout the year. So for the annular, this is a track of the annular, this gold circle track. It covers most of San Antonio, so if you're within the city, you're probably going to be fine. But I will stress that for the total solar eclipse, where you'll see something like this, you have to be in the right place. If you are on the wrong side of town, you will not be able to see totality. So you do have to be on the right half of San Antonio. Please do go online and make sure to look up where is best to see it within town, or if you want to go out of town, certainly find your way more up towards Fredericksburg in that area. That'll be a nice area, and be able to make your plans early for this. Oh yes, and we do have eclipse glasses. So for that annular eclipse coming up in October, That's one where you will have to have the glasses to see it, because the moon will not completely block the sun. It will just move to the center. It's so far away that the disk doesn't cover up the sun entirely. So make sure to have those solar eclipse glasses for the one in October. And then finally, I'm just going to leave you off with a couple of really beautiful images that have been released recently. I couldn't make a whole story out of them, but they are very nice. One is this infrared band image from the European Southern Observatory Vista telescope of the L1688 dark nebulae region, right there. Very, very beautiful image. And then there's this James Webb Space Telescope image of NGC 5068, and a really, really beautiful detailed view of the spiral arms of that galaxy. Please go online and look for these images in detail. This is just a sampling of what is available on this. So once again, thank you, and we'll go ahead and move on to our next speaker. Thanks a lot.
Thank you. That works. All right. Thank you, Caleb. So hopefully those of you who have been here the last few times already recognize our next speaker, Aaron. Yeah, all right. So Aaron is a San Antonio native, born and raised. He obtained his bachelor's degree in physics from UTSA. Go Roadrunners. All right. And continued there for graduate school, eventually joining the UTSA SWIRI Joint Graduate Program. And without bias, I can say he's one of the best grad students in the program. Aaron's research involves asteroids, specifically characterizing near-Earth asteroids and the interior binary asteroid called Atira, which you're going to hear about just now. So go ahead, take it away. Let's hear it for Aaron.
Thank you for reminding me. My word is asteroid, so I recommend stock up now. What was the word? Is that a trick question? Asteroid. All right, we've all got around to practice. There we go. Okay, so yes. Yeah, it's good. I can see what's coming next. Oh, wait. Okay, counterintuitively, down is next. I guess that kind of makes sense. Anyways. Okay, so the topic of my research will be the topic of my talk today. I use observational data and modeling software to characterize a binary asteroid called Atira. And hopefully, I did not see that one coming. Hopefully, by the end of my talk, we can all understand what's going on with this slide. All right, so a little bit of motivation first. Why do we want to study asteroids? Well, simply put, they are laboratories out in space that we can look at, that we can study, that let us know a little bit about the early solar system and where we came from and how we got here, essentially. And also, so interior asteroids, like Atira, it is, they tell us about the dynamical evolution of asteroids. And what I mean by that is, I told you, it's front heavy. So what I mean by that is, the interior asteroids, they more than likely got there somehow, some way. They moved inwards. And I will show you what I mean in a minute, specifically by interior, so we're all on the same page here. And, of course, so Atira is a near-Earth space rock that comes pretty close. And it's a good idea, it's a smart thing to do to know about the space rocks that come close to us. Anybody, you can go ask the dinosaurs or not, because they're not here, so there you go. That's why we want to know about them. And so a little bit about Atira. It was discovered in 2003 by a survey program put on by the Lincoln Laboratory, and then in 2017 it was confirmed, or rather almost discovered, to be a binary asteroid. And so this is what I mean by interior. So the blue ring you're seeing here on screen, that's the path that Earth takes around the sun. The sun is at the center of the yellow crosshairs in the center. The purple circle is Venus, the magenta circle is Mercury, and that white circle, that is Atira. And those white vertical lines help you understand how high and how low it gets below the plane of orbit of the rest of the planets. So what that means is every now and then it gets really, really, really high above our plane. So you would almost be looking like upwards if it was near us, relatively speaking, and sometimes it gets a little low. But nonetheless, its entire path around the sun is completely interior to the orbit of Earth, and that's interesting in itself. And yeah, so why study Atira? It adds to the knowledge of the Atira class asteroid. So this was the first one discovered to orbit completely interior to Earth. Thus, the class name was named after Atira. We understand a little more about how those interior space rocks fit into the rest of the asteroid population as we know it. Ha, gotcha. And then also, it's big and close. Ask the dinosaurs. Okay. So then, now we know why we want to study Atira. How do we study Atira? So we need some kind of information that tells us a little something about the size, about its dynamical evolution, about the relationship with its companion, and maybe, if we can, what we can learn about its shape. And there are two observational methods we can use that do a good job of getting those things we want to know. That is light curves and radar. So what are light curves? So light curves, so they originate by an observer uses a telescope like the Ondrahov telescope pictured here. That's one of the telescopes that actually one of our colleagues uses for the light curves that he graciously shared with us. So they use that telescope with a camera on one end, and they look at an asteroid. This is not Atira. This is just an example of an image of what a space rock would look like floating through the sky as we would see it. And what we want to do is we want to measure how bright that object is at certain times. And that's what a light curve is. So don't worry, I got it all up here. So essentially, when it comes back on screen, you'll see what I mean. But we want to know how bright an object is over specific time periods. And so astronomy is a little weird. When it comes back up, I'll be able to explain. Switch. There we go, back on track. Okay, you got it. One more. There we go, okay. So astronomy is a little weird in how we do things. So on this graph, the brightness, okay, so we all got that graph in our mind, right? So the brightness, the things on top are brighter, or rather, I should say, the things nearer to the top of the graph, the data points, those are brighter than the lower ones. It's just a weird thing that happens in astronomy. You get used to it, whatever. But the point is, it's a curve of how bright an object is. It's a light curve. So that's one way we obtain information about an asteroid. And the next way we obtain it is very important to my research, and I really want to wait because I got good pictures. That one, yeah, there we go. I'm sorry, I summarized what are light curves. So they are, yeah, we're good there. So they are collections of observations telling us how much optical light, so the light that we can see, came from an asteroid at a specific time. And with light curves, we can roughly determine a space rock's spin period. So how fast it spins, how long it takes for it to spin around one complete revolution. And if there's a companion, like there is with Atira, we can better understand its relationship with its companion, and specifically how long it takes for that companion to go around the big one, what we call the primary. So how long it takes for that to happen. And then for Atira, so this is one caveat that makes studying interior space rocks really, really difficult. They are interior to Earth, so that means we're almost always looking towards the sun whenever we want to observe it. Now, I challenge you to go find a star at high noon, and you get back to me and tell me how easy it was. That's along the lines of why it's difficult to get this kind of data. So next up, the next observational method we can use is called radar. So radar is an acronym. It stands for radio detection and ranging. There we go. Now you see where the letters come from. And so we take a radio telescope like the Arecibo Observatory, and we send out a signal. We send out a radio signal to an object, and we see what comes back. And there's a little graphic here that I found that is perfect. So that peach amorphous blob up there, that's an asteroid. It's spinning. And so we're going to watch here. So we send out a signal, As it comes back, it changes a little bit. So the wavelength of that signal that was sent out shortens and widens depending on where it hit the asteroid, and it comes back at different times. So the part of the signal that bounces off the part of the space rock that is closest to us will get to us sooner. I hope everyone understands what I meant by that. And as it spreads out around the asteroid, as that light spreads out around, that signal comes back just a hair of a bit later, and we can see when that comes back differently. And just for a point of reference, so those yellow arrows on the left at Arecibo, that's called the Gregorian dome. That's where the receiver and the transmitter is. So the signal comes from that spot, it goes down into the dish, and then it comes back up, and then we receive the signal it comes into the dish and goes up to the receiver. And then that would be equivalent to where the yellow arrow is on the right graphic, just so we're all on the same page here. Also, I want to throw in a fun fact, because I learned this, and it blew my mind when I learned. So Arecibo, I've always thought it was made of concrete. I always thought that dish was made of concrete. It looks white. I go walk on a path, that looks white, it must be concrete. It's not concrete, it is 38,778 perforated aluminum sheets of metal. It's not concrete, it's metal. And I had to have a conversation with my friend. I was like, but why is it concrete? And he was like, it's not. I'm like, yeah, but why is it concrete? And he's like, it's not. And I'm like, I don't know. But anyways, I digress.
I got some more bad news for you.
Oh, yeah. I got to witness firsthand a couple of weeks ago, so yeah. And so there's a specific kind of radar data that we can get back called a delayed Doppler image. So what we're seeing on screen, it's not an optical image. That is radio. So it's called a delayed Doppler because on the vertical axis we have delay. So as we go from the top of the image down, it gets farther and farther as we go down the image. So the secondary is this little dot of light right here. So it is further away than the cusp of the primary. And we can tell that by it's just literally lower in the image. And then next, we have the Doppler, which is how much the wavelength of the radio signal we sent out changed. So it'll get a little bit shorter, it'll get a little bit wider. And as we go to the right, that means the wavelength got a little bit shorter as we go more to the right. And then we're gonna watch the secondary move where the red arrow is, so it's moving up and to the right. So that means it's getting closer and it's getting faster because there's a specific relationship when we say that the frequency increases of a wavelength. Rather, when we observe a signal, if that signal shifts and gets squished together, so the frequency increases, that means it's getting faster. That's what we call blue shift. And it's just a fancy way of saying it gets faster. It gets faster. I keep pointing to the wrong space. And then the next kind of radio image, it's less like an image, more of just like a thing that we can do with the data and that we can see visually. It's called a continuous wave spectra. So essentially, if we were to take that last image and flatten it completely, what we would have is a continuous wave echo spectra. So that big spike in the middle, that's the secondary. And what that's saying is, there's a lot of frequency coming back from that space. And it was near the center of the asteroid, which is where 0 is. And so we want to know how fast, which is related to the Doppler shift, to the frequency, we want to know how fast certain parts of that object are spinning. So on the left, it's spinning it's minus, so it's spinning towards us. And on the right, it's spinning away from us, so it's greater. And then I think, yes. And so the vertical axis just tells us how much of that signal returned to us. We call it echo power, and the higher we are up on the vertical axis, the more signal we got back. And then I want to throw one equation at you, and I'm going to read it out loud, and don't pay attention to the words I say, but it's B equals 4 pi cosine delta over lambda p. Now those are just fancy names for symbols, but what we're seeing is, so the B stands for bandwidth, and the bandwidth is literally how wide this band is. So this mountain, how wide it is, that's the bandwidth. And so what we can learn is 4 pi, that's just a number, just some number. Cosine delta, that's telling us how much of that signal we can see, basically, based on its orientation in space. And then over lambda p, so lambda is wavelength. We know that number. It's 12.6 centimeters. It's always the same if we observe with that wavelength. It comes from Arecibo. And, gotta catch my breath. Okay, and then the p, that's the period. And so if we rearrange this, this equation, I didn't do it on here, I should have done it. But if we rearrange, we can solve for the period, which is we can know how long it takes for that asteroid to do one revolution simply by measuring the width of to measuring the bandwidth. So we get one piece of information just by one observation. But I will say it's a rough guess. It's not perfect, you gotta do more stuff. And so summary, what is radar? It's an acronym, and it's a collection of observations telling us how long it took the signal to return and how the signal changed upon returning. And with radar, we can to a very good degree, determine how big an object is. And maybe the spin period, like I said, there's a couple of factors that are depending. And then one interesting fact, so with radar, and astronomy specifically, it is the only observational method where we are measuring a signal that we sent out. Like Dr. Schlegel was saying, they measure X-rays that are coming from space. With radar, we send out a signal and we measure what comes back. So it's a pretty cool way to observe things. But again, since we have to send it out, it's got to be relatively close. And the farther away it is, the more complicated it gets. So now, so the modeling software I used is called SHAPE. I should have looked up what it stands for, but it's pretty straightforward. You put in light curves and radar images like we just learned about. You put that into SHAPE, and there's dozens and dozens of knobs and buttons that you can change and tweak to do whatever you want. And then out pops a 3D model, just like the one on the right that is spinning. And I'm going to be honest, I barely know how SHAPE works. It is essentially a black box to me because it is so complicated. There are so many parameters. I spent a year using this software, and I still have, I don't even know, a mountain worth of information left to learn. Anyways, okay, so how do I use SHAPE? So what I want to do is I want to run tests to see how fast the asteroid is spinning and how, there we go, somebody's paying attention, how fast the space rock is spinning, and also where the space rock is pointed. So that's the rotation period and the pole orientation, and I combine those to make a multifaceted model. That's just a fancy word for saying, so you get a sphere, you plaster on some triangles onto the surface, and you push and pull the corners of that triangle. And so the facets are the triangles, multi because there's a lot, and it's a model because it's not real. So you just have this shape of a bunch of polygons on the surface that you can push and pull, that shape pushes and pulls to get out a 3D model. And then I have like a little graphic here, so it's mostly to say I slowly add in data over time. I go from when we are near the radar observations from Arecibo to further in time with the light curves. And it's just because we want SHAPE to have a good time when it gives us the models back. We don't want to make it angry, because it will get angry. And so I want to peel back the curtain a little bit of to what the research process is like. So when I say I want to run, or I want to know what the pole orientation is, so this graph we're looking at, this is literally a map. So Earth has latitude and longitude. You can look up your coordinates for anywhere on Earth, and so if we were to blow that map up and paste it onto the sky above us, that's exactly what we would be looking at here. It's called the celestial sphere, and it's a little bit different. It's tilted in a different direction. It's aligned a little bit differently, but for all intents and purposes, there's a latitude and longitude much the same as there is on Earth. And so what I do is I say, okay, let's just model the whole freaking thing. Let's put a dot everywhere over the celestial sphere, almost everywhere, and see what comes back as a good fit. And so on this graph, we're seeing the darker the color, the better the fit. And then as we get a little more knowledge of what's a good fit, we zoom in and we run more tests, and we run more tests, and we run more tests, and so that's why we have these globs. And eventually we identify it's a good orientation. It could be pointing in that direction, maybe. And then, so when I run a rotation period test, so what we're seeing here on the horizontal axis, it's just a different way of saying it, but it's the rotation period. It's just a different kind of number. And essentially what this graph is showing you is that we did a sanity check to see could the rotation period, so how fast the asteroid spins, could it be, someone's paying attention, so could it be this number, could it be this number, or is it the number we think it is? And the lower you go on the vertical axis, the better the fit. And so this is just a way of saying we confirmed what we thought we knew, but we wanted to make sure. And then this is where the graduate part comes in. I get the joy of looking at hundreds of models with my eyes and say, does that bump look good? Does that bump look good? I don't know. What about this bump? And I do that many, many times. And I compare models. So these are two very favorable models that we have right now. And if I'll explain what the panels mean. So on the leftmost panel is the observation. So that's the data that was taken from Arecibo. The second from the left panel is the model. So that's what shape spit out. That's what it says. It might look like this. And then the third from the left, the residual, we subtract those first two images from each other, and we get a little something left. And that kind of tells you how good of a fit it was. And then the rightmost panel is the 3D model that it spits out and says, yeah, it probably looks a little something like this at that time. And so I look at, so there's 6 on screen. I've looked at, I don't know how many of these freaking things. And it doesn't stop there. It doubles. I do the same thing with the light curves. So that was just radar. So I go and look at all the bumps and the squiggles in the light curves. And again, I compare models. I say, does that bump look good? Does that bump look good? I don't know. What about this bump? And so I've been doing this for a year, and I've developed an intuition of what is good and what is not good. Where does shape have a problem? And so like, okay, we ignore that. And where does shape have a good understanding of what it can and cannot do? And so we focus on those areas. And so these are examples of light curves that we would focus on because there's specific bumps that we want to replicate in the model. And so with all that said, where are we at? So we have 2 models that we think are most likely it. However, they're very different from each other. So the model on the left, that one's 5 kilometers wide. That's about 3 miles or so. And the model on the right, the asteroid on the right, there we go, wake him up. So the asteroid on the right, it's about 7 kilometers, that's about 4 miles. And would the asteroids point in different directions? Like would good models point differently? Maybe, it's not that weird. Should they be very different sizes? Maybe not, that's a little weird. And so we're having to do more work to determine which one is it more likely. We can't say with 100% confidence, yeah, it's that one. We can only say it's most likely this one based on this evidence. And we have one trick left up our sleeve that we want to do. So what we're doing now, actively, I literally did this morning, we're combining the primary and the secondary. So the whole time that I've been doing this research, up until literally like this week and last week, I consider them separately. So I have the big rock, I got the small rock, they probably look like this, they probably look like this, probably point in this direction. And now I'm combining them to say, at this time, when we took this observation, where were both of them in space? And so, the leftmost panel is the observation, second is the model, and what we see is, we're running different things to see, is it this or is it that, basically. We want to know, where do the orbits line up? So where do we get the same kind of look depending on where the secondary is relative to the primary? And that's what we're doing now. So we have one trick left up our sleeve. And a little bit about what I've learned. So that was about shaping the future. Now talking about shaping my future. I've learned how to use shape, kinda. There's a lot more to learn. It's a beast of a software, and it takes the people who I have the pleasure of working with. They've been doing this for years, and I'm the last on the bus. As we were talking about earlier, if you don't know, that telescope, Arecibo, it collapsed, so it will never be used again. And I got to go there a couple of weeks ago, like one of the last people, or rather one of the last science trips that will ever be at Arecibo. And so it's, I don't remember where I was going with that, but yeah, it sucks. And one of the other things I learned is, I've learned how to embark on the scientific process. So one thing we always are told in class is, be careful of how you use your data, because the way you use it, your methods, will have implications on the conclusions you draw. And you have to be aware of what you're doing. And you get told that, and you're like, yeah, I got it. And then you go and use your data, and you realize you've run up to a wall where you're about to make a conclusion that drastically differs from how you should actually make a conclusion. What I mean by that is there are ways I would use the data that I wouldn't even be aware of that would put me on a path of drawing a wrong conclusion. And you don't realize that until you get experience working with the data. And thankfully, I have a great advisor that can put me back on the right track and say, like, you know, like that's a direction you don't want to go down. And so, yeah, that's one of the key things I've learned from this research project. And then I'll take those skills with me to the next project because I got a couple more years left in school. That's all I got. Thanks for listening.
Thank you, Aaron. That was a fantastic talk. Really, it was. And is that a bump? No. So we have a lot of questions for you here. Everybody was very interested in what you had to say. So, what's the difference between a very large asteroid and a very small planet?
Ooh, that's a really good question. You got to ask NASA for that one. So that honestly will come down to the way we as a science community defines things. So the biggest asteroid that we know of, I think it's probably the biggest one, it's called CIRRUS. And it was one of the first ones discovered because it's so big. I don't know the size of it, but I want to say it's comparable to Mercury, which is a planet that is near the sun. It's pretty freaking big, and which is why it was one of the first ones discovered, because it's really bright in the sky. But so a small planet and a really big asteroid, it really depends on where it is, how has it cleared its path. These are the definitions that the IAU put out of what a planet is. Has it cleared its path? Does it have hydrostatic equilibrium, which means is it round? So yeah, that's how you can determine is it a big asteroid or a small planet. Oh yeah, that's a picture of some of the grad students I met. We went down by the dish. Yeah, that is the state of Arecibo at the moment. Yeah, we're the up and coming in the field. No, it's actually, it kind of probably is fixable, but the NSF said no. Yeah, boo. I hope NSF isn't here.
Yes, I remember the video when it happened. It was quite tragic. The asteroid belt, which I know this material is not in it, but the asteroid belt, why is it where it is between Mars and Jupiter, not somewhere else? Why isn't there a second one?
That's a really good question. I don't know. If I were to have an educated guess, it would have to be to do something of where the planets are and what was left over when those planets kind of confirm their spot in the solar system. And what you have left is just a path of a bunch of rocks that never quite formed into a planet. So Sirius is in the main asteroid belt. And so could that have been a planet? I don't know. That's why we study asteroids. But to go back to the question, I honestly don't know. But actually, now I'm interested to know what the case is. Tracy has more to say.
Yeah, no, very good educated guess. But yeah, a lot of it has to just do with the positions of the planets, and Jupiter's gravitational influence is really what keeps the asteroid belt where it's at.
Yes, poor Pluto. Speaking of planets, poor Pluto. From the light curves, can you back out what the albedo of the asteroid is?
That's a good question. Somebody knows what the word albedo means. I barely know what that word means. Again, I don't know. I don't know if you could back out from a light curve and get the albedo. However, when you observe an asteroid, if you know where it's at, and you know it's, if you know where it's at, you can, if you know where it's at, and you know what it's made of, you have a good understanding of what the albedo is. However, again, those are compounding factors that all have to line up when you observe the asteroid. But to go back to the question, I'm not necessarily sure if specifically from a light curve you can back out and get the albedo. I think you would get the albedo before you would do the light curve, I think. So that would be something you know without needing the light curve, I think.
Right, I like this question. This is a good one. Does the composition of the asteroid affect how the radio waves would be transmitted back to us?
Yes, definitely. So there's a common definition that a big ball of metal out there, a big spherical ball of metal, it would bounce back almost perfectly. And what I mean by that is the radio signals that are sent out from Arecibo, they have a polarization. So they're spinning a certain way. And we want that because when it comes back, it tells us a little bit more information. And if you had a perfect spherical metal ball out there, the signal would come back perfectly anti-polarized. So the signal would come back completely opposite, like 100% effectively opposite. That would be a perfect reflector. Asteroids are not perfect reflectors. They're usually rubble piles. And depending on how big the chunks of matter are in the asteroid will determine how the signal comes back. So yes, the composition will definitely change how the signal looks when it comes back to us. Oh yeah, I whited it out because I didn't want to distract y'all. But behind the whiteness, we took a fraction. So the bold line is the opposite circular polarization. So the stuff that bounced back perfectly. And the dotted line is the same circular polarization. So that means it bounced at least more than once. So you can kind of picture if you see something spiraling and it bounces, takes a 90-degree turn, and spiraling takes another 90-degree turn, you're now oriented the same way it came back. And that's interesting. But again, that depends on how big the rocks, how big the component, or not the components, how big the rocks are that make up the rubble pile of an asteroid, if it's a rubble pile. And there's a lot of compounding factors when you take the fraction of how much came back with the same polarization and how much came back with the opposite polarization. But that can put you down the path on having an educated guess of what the asteroid is made of. So certain fractions will mean it probably is made of this or probably made of that, basically.
All right, one more, one for the road. If not all asteroids have companions, does that mean that some of them get lonely?
Well, I don't know, maybe. I think I know who asked this question. Yeah, the ones who have companions, they're probably not lonely. However, they probably have very little understanding that there's a companion, not because they're unsentient, but because the big one is a lot bigger than the small one, and there's very little interaction with the small and the big one. However, do they get lonely? I don't know. We got to go out and ask one. We've been to 2 of them now, so we got to go out and do more. That's why we study asteroids.
Another round of applause for Aaron. Thank you. Well, don't go too far because we've reached the end of the main program. Let's thank both of our speakers now, Eric and Dr. Eric Schlegel and Aaron Deleon. So there was a lot of great questions that I wasn't able to ask Aaron. If you were the ones that asked them, you can come up and ask him yourself during this next break. We are going to take a short little 5-minute break and begin our trivia. If those of you who want to stay, we will have our trivia. We'll be passing out sheets, so just bear with us while we do that. And like I said, it should take around 5 minutes. In the meantime, come look at our merchandise if you'd like. Student, scientist, postdoc, whatever level, you may participate, but you may not win. But just let me know on the sheet that you're ineligible, and then we'll put you on a separate pool against the student. You can participate by yourself. Gotta make it fair. All right. Everybody ready? All right. Question one. Question one. One. No. Push the button. The Zia Pueblo are an indigenous people that revered the sun with the symbol below that can be found on which U.S. state flag? Is it A, Arizona, B, Nevada, C, Oklahoma, D, New Mexico, or E, Utah? Which state has this as their flag, on their flag? Yeah. No, I'm taking them all. No. You're kicked out. You already spoke.
Yeah, I know.
That really was. As somebody who you did a very good job. Very good.
Thank you. That's a really good honor. Yeah, I didn't plan on it, but it ended up being the science talk. But I'm glad to bring it down.
Yeah.
Bring it down to this level. And also, it's a good way of practicing. You know, like what do you know? What do you not know?
Exactly. Everybody good? Yep. All right. Question 2.
Larger than life. What is the largest asteroid in the solar system? This is technically a memory recall because I kind of said this in one of the questions, actually. Is it A, Vesta, B, Ceres, C, Gamarian? Is that a... Anyways, D, Pluto, or E, Pallas? Yeah. Oh, yeah. Asteroid. I will emphasize asteroid for this question, which is the largest asteroid in the solar system.
We all know it's Gamarian.
Texas.
You can put it down. Wait, what? Is it Pallas? Oh, Dallas. Yeah, that one. That was a stretch. All right, everybody good? No, I'm sorry. Everybody good? Question 3.
X radiation, or X-rays, named after the most common unknown variable, was first discovered by which scientist? A. Hans Geiger, B. Wilhelm Röntgen. What? Well, I said Wilhelm. I was close. Wilhelm. Wilhelm Röntgen. There we go. Enrico Fermi, J.J. Thomson, or Albert Einstein? Or is it Einstein? I have no clue.
It's technically Einstein.
Who discovered X-rays, basically? That's the question.
I've heard you don't like him when he's angry.
Everybody good? Yes? All right, question 4.
Pierce Brosnan and Sean Bean duke it out at the Arecibo radio telescope in which hit 1995 James Bond film? Is it A, Die Another Day, B, The World Is Not Enough, C, Tomorrow Never Dies, or D, GoldenEye?
If you don't get this, boo.
Yeah. I think for the most part it would be considered an easy question.
don't know it?
All right. Everybody good? Next question.
Numero 5. What is the total mass of all the asteroids combined given in percentage of the moon's mass? So there's a lot to unpack here, okay? But is it 3%, A, B 30%, C 300%, or D 3,000%?
All of them.
Every asteroid in the solar system, our solar system. There may be asteroids in other solar systems. We don't care. Our solar system. Are those asteroids?
No.
I mean,
The Kuiper Belt.
the Kuiper Belt objects are Kuiper Belt objects. KBOs.
No, not all of them are TNOs.
No, there's
Are all of them TNOs? No, some of them are. There's TNOs and KBOs.
ASTN, yeah. And then centaurs. Percentage of the moon's mass, our moon, the Earth's moon. M should be capitalized, Sam. Yes. All right, everybody good? We'll move on to question 6.
Which astronaut commanded the space shuttle flight that deployed the Chandra X-ray Observatory in 1999? Is it A, Neil Armstrong, B, Eileen Collins, C, Judith Resnick, D, Gene, I don't know, that's Cernan or Cernan, or E, Bill Nelson? Did anybody go to the AOT back in, I don't know, was it 2020 when Eileen Collins was there? 2019? Yeah, I think it was right before the you-know-what. I think it was that February, actually, like right before. In the before time, yeah. Eileen Collins? Yeah. Everybody good? Bonus question.
All right, today's bonus is about moons. We talked about companion with an asteroid, so today's about just moons of our planets. Only 6 of our 8 planets have moons, and we would like you to list them in descending order, so most moons at the top, least moons at the bottom, the order of which they have moons. The first hint is that the answer is not the same order as the size of the planets. So just because a planet's really big or really small doesn't mean it follows common logic of how many companions it would have. And then the second hint is that Pluto doesn't count because the IAU sucks. Just... Oh, you didn't put it.
This answer I got from solarsystem.nasa.gov/moons, and it was updated May 23rd of this year. So very recent.
Thank you, Sam. All right, so we'll leave this up for a little bit. When you all are done with this, you can come up and bring your trivia sheet, and if you borrowed a pen, bring the pen with you, and then we will start to grade them, and then so we're on a little mini break until then. And don't forget to come check out our merchandise if you're up here and get your eclipse glasses.
Does anybody need any questions repeated? Going once? Going twice? Soul. We're going to come around and pick them up. If everybody could hold them up and also give back the pens, that would be greatly appreciated. Or actually, I'm sorry. If you could bring them up to us, please. That would make it a little bit easier. Thank you. All right. We've got everybody graded. We're going to go through the answers now. I'm going to take my time because we're trying to get the prizes sorted out, actually. We had some stickers get lost in translation.
I want to say that I'm mildly disappointed in the answers. Very mildly, because, you know, I'm glad you all participated. But, come on. All right, so the first question tonight, which was about, this doesn't work. Which was about the New Mexico, or the flag. At least I didn't say that. New Mexico, flip it. At least I didn't make this mistake when I read the question. At least I didn't make the mistake when I read the question. The flag is of New Mexico. So for those of you that said D, which most of you did, congratulations. Thank you. Question 2.
I don't remember what it was, but the answer is Vesta. I apologize. I might have led some of y'all astray because I think I did cover my own. I will say I think I covered my own arse by saying it's one of the biggest. But I apologize. I think we'll consider bumping up everyone's trivia by 1, but that actually doesn't do anything. So the winners are still the winners, even if we bump everyone's questions up by 1. So
Look what you've done.
and look what you made me do. Ask Sam.
According to Sam, Ceres is not an asteroid.
Oh, that's a.
Unfortunately, it was a trickster.
Take all your suggestions up with Sam.
All right. Question 3, which was about who discovered X-rays. The answer was, of course, the one that I can't pronounce. B. Wilhelm Röntgen. Röntgen.
Wilhelm Röntgen. That was probably terrible. All right. The James Bond film. Which one was it? GoldenEye.
R.I.P. Tina Turner, who sung the intro to that movie. Yes, R.I.P. Yes. That's a good song, by the way. That's a good one. All right. So the next question, 5, which about the total mass of all the
Oh, no, go ahead. Sorry.
of all the asteroids in our solar system.
I know I graded everybody's, but I want to see just a general guess. Did you think it was heavier than the moon? Oh, the sum mass of all the asteroids? And who thought it was lighter than the moon? 3%. 3%. You add up the mass of all the asteroids, it's 3% of the moon's mass.
They're really tiny. They're like pebbles in the grand scheme of things. Even when you put all these pebbles together, it's still a small little rock.
That's a testament to how big the moon is, really.
Yeah, our moon's actually pretty big.
Hey, so does that number include series? It doesn't change.
I know, even if it included Sirius, I don't think it would bump it up to 30%. Wait. Oh, I see what you're saying.
I mean, everybody just, when we're done here, just go up to Sam. I mean, all right, the next question, which was about the, this was your.
Oh, yeah. Question 6, it was about which astronaut commanded the space shuttle for the Chandra X-ray, and I think I pointed to everybody. It was Eileen Collins, even though I did not know that. I was just asking if everybody went to that AOT. But yeah, it was Eileen Collins.
AOT number 19 at the Whitty Museum. Those of you who were there, remember it was a really fun event, and hopefully we'll do another Whitty thing soonish. Everybody seemed to enjoy it, right? That was a good one. So we should go back. That was Eileen Collins, commander of Chandra. We had a whole Chandra talk. She talked, and then a Chandra scientist talk, and X-rays, as we talked about today. Very interesting stuff. So now we get to the bonus. The planets in order of the amount of moons that they carry. I will tell you, the largest planet in the solar system is Jupiter. The one that has the most moons is Saturn. The full list is Saturn at 146, Jupiter at 95, Uranus at 27, Neptune at 14, Mars at 2, and Earth at 1. Venus and Mercury, of course, have no moons whatsoever. Yes, well, we always use the bonus generally as a tiebreaker. That's our tiebreaker. But oddly enough, and this happens to us a few times, and Sam, I asked you to get stickers. There we go. NASA stickers are great. As happens before, we have a tie for third place. So we will just give both teams the same prize. We can't differentiate the tie between these two. So, I'm glad this one won, because this one's going to be fun to say. So I'll start with the first third place winner is Space Rocks. Congratulations. All right. You get a Celestron, you get a NASA sticker, and a Celestron case that has plugs, chargers in it for all your, courtesy of Robert Reeves, who always brings us great stuff.
And Team Orange.
Team Orange. The second third place winner is Bad Batch. There we go. It's a good show, too, Bad Batch. Yes, you also win the NASA sticker and Celestron charging case. Congratulations. Now we move on to second place.
Place. That thing. Oh, okay. So, second place. Winning a Celestron beanie and also some NASA stickers. Spectra Maximus.
All right, and this is our answer key. The answer key won, guys. No. It always wins. All right, so our first place tonight, who y'all got 5 questions right, so great job. I think the only one you missed was the damn series one. And you didn't get the bonus correct, but you still won. And you will be receiving a Celestron, what is that called? Tumbler?
Yeah.
Tumbler mug, coffee mug. 365 days of the moon. Oh, yes. Yeah, of course.
This was combined from last month's second and first place.
Yeah. You get it right back.
Once again, at least the first place prize winner was here. 2 or 3 AOTs ago, they left. We had nobody to claim it, so thank you for being here. And thank you all for coming. That's our event for tonight. Thank you. Our next AOT will be on July 5th. We will have some very good speakers then as well. Yeah. And be sure, most of you have tabbed out already, but make sure that you tip your waitresses very well. They always do a great job here at Blue Star. Thank you, Blue Star, for hosting us. And thank you to Swiri for supporting us. And sign up for our email list and follow our socials if you haven't already. And
one quick announcement.
Hi, everyone. My name's Izzy. I'm a violinist in the Symphony Viva Orchestra here in San Antonio. I don't know if any of y'all know that we have like a community semi-professional orchestra, but we're playing Holst the Planets this Sunday at 4 p.m. It's at University United Methodist Church. So you're all welcome to come. You can search us by just Googling Symphony Viva, social media. We're there. So hopefully see y'all. It's this Sunday at 4 p.m. at the University United Methodist Church. Thank you.
Thanks.
thank you for that. And thank you all for coming again. Please come look at our merchandise before we wrap it up and get your eclipse glasses if you haven't already. We will see you in July.
If you want to touch a shape-modeled asteroid,
Oh, yes. Come see Shape in action.